The thing that always fascinated me about Ebola, I really got into this actually reading The Hot Zone, was how this virus, appears out of nowhere, kills a bunch of people, and then just disappears back where it came from without a trace.
And we can label it with DID.
So I've been working on Ebola since about 2003. I have to say the part of my job that I love the most is coming into work and hanging out with a bunch of really smart people, getting to engage them about the science we're doing towards our common goal of learning more about Ebola and how to combat it, and sort of feeding off of their excitement. I'm not saying every day is like that, but that is my favorite part of the job. So you can think of the virus as this burglar that's learned how to break into this really fancy mansion that has lots of security, and it's evolved to exploit the genes and proteins and mechanisms in your own cells. It knows where all the security cameras are, it knows which wires to cut. But here's the thing, each of those potential proteins in your body that are being used by the virus is an Achilles heel that we can target to prevent the virus from infecting you. So this is a really classic picture of what Ebola looks like. That's not really how we think about Ebola. We really think of it as this complex molecular machine that's really got two pieces. It's got the payload, which is really the genetic code that allows a virus to take over your cell and turn it into a virus factory. And that code is delivered into the cell by the delivery system, which is the membrane of the virus, in which are embedded molecules of the spiral protein called the glycoprotein. So together with the membrane, the glycoprotein almost acts like the delivery system of a rocket that needs to deliver the payload.
If it's going to cleave here,
right,
why doesn't it cleave here too?
I'm going to show you some of the strategies we're using to attack Ebola. But first, I'd like to show you exactly how Ebola infects a cell in your body. First, the virus has to convince your cell to engulf it. Then, the cell takes it up into a membrane-bound compartment called the lysosome. But Ebola actually needs to get out of the lysosome for two reasons. The first reason is that the lysosome is filled with enzymes that can destroy it, but also the virus has to get into the cytoplasm because that's where all the goodies are that it needs to copy itself. And the way the virus escapes is by fusing its membrane to the membrane of the lysosome. How does the virus know how to do this? So it turns out that the virus is actually receiving signals from your own cells, telling it when it's in the right place and when it's the right time to carry out this fusion reaction. It's almost like a GPS system. And it turns out that one of the most important components of this GPS system is one of your own proteins called NPC1. The virus has evolved to use NPC1 to bind to it and use it as a part of its orienting mechanism that tells it, okay, fuse now. And when that happens, Ebola essentially releases its payload, the genetic material, into the cytoplasm to kick off the replication process. So there are different ways in which we can attack the virus and prevent it from infecting the cell. The first is to go after your own cellular machinery that the virus has evolved to exploit. And so we're trying to develop drugs that prevent the virus from binding to NPC1. If we could prevent the virus from using NPC1 in this way, the virus eventually gets ripped to bits inside your lysosome because it can't get out. And this is exactly what we want. The second approach is to actually go after the virus itself. One of Ebola's Achilles heels is its glycoprotein. If we take a closer look, you'll see that the glycoprotein needs to move. It's a highly dynamic structure, almost like a gymnast doing a routine. And so here what you can do is you can create proteins called antibodies. The antibodies act like these burly wrestlers that can hold down the arms and legs of the gymnast and prevent them from moving apart. And this is enough to block and kill the virus. So we're actually working closely with John Lai here at Einstein.
13C6 comes straight from the top.
Along with a number of scientists all over the world to develop cocktails of these antibodies that could be used to target and have a treatment for all the different strains of Ebola. So our lab doesn't actually study live Ebola. In order to work with live Ebola, you need these high biocontainment facilities, and there's only a few of them in the world. Instead, we take advantage of the fact that the virus is a highly modular entity. We can take a virus that is not harmful, called VSV, and replace its delivery system, its glycoprotein, with the glycoprotein from Ebola. So it has the Ebola delivery system, but its payload is actually this innocuous genetic material of VSV, sort of like a sheep in wolf's clothing. This is a great system to safely study exactly how Ebola invades cells. I then pick up the phone and call my collaborator John Dai at USAMRIID, who does have that high biocontainment lab, and he can then take the findings that we've made using our VSV surrogate system and then confirm them using the live Ebola. I'm actually quite optimistic that there will be a treatment or multiple treatments for Ebola in the next 5 to 10 years. Even from this outbreak, there are some promising potential therapeutics that have come forward. I think there's still a lot of work to do. I think there are lots of ideas, but the development work of really making a therapeutic that's safe, that can be distributed to lots of people, that's highly effective, that can get all of the FDA approvals, that's a long, hard slog, and I won't say that we're there. I mean, we still have a lot of work to do, but I'm optimistic.